We're going to be talking about here are logarithms. So I know a lot of people get afraid about logarithms. They just don't know what's going on with them. And it's just a regular function like any function that we have in math. The only thing is that logarithms and exponents are inverses of each other. So in order to solve an exponential problem, like b to the y equals x, we need, if we're solving this for y, we use logarithms in order to solve that problem. So notice that logarithms have a base, this little subscript here, this is base b, so it's log base b of x equals y. If and only if b, that base, is positive, which is greater than 0, that number on the inside is also positive, and b shouldn't be 1. So really we could have said here that b has to be strictly greater than, or actually no, it can be between 0 and 1. It can be a fraction, but it can't be 1. So there is another way that we've already talked about and reviewed on how to solve a problem like this. What we could do is we can log both sides. So if I log both sides here, so we get log of b to the y, that's not base b, that's just of b, equals log of x. What that helps me do is that that exponent then comes out in front, which is this power property we have here. And if we're solving this for y, like this is y equals, you end up getting log of x over log of b. So the reason I'm showing you this is because certain calculators cannot just type in like something that looks like this. So for example, in your calculator, in your graphing calculator, if you go to math and try to find log, or actually our log base, which is down here on A, you can either do alpha A or something like that, or some calculators are different. But in the TI-84 Plus, if you find log base, you can actually plug in things like, log base 2 of 4, which is 2. But if you don't have that and you just have a log button, like the normal log button right here, if you press log in the calculator, this is default base 10. So what you can do is instead of doing log of base 2 of 4, you can do log of 4 divided by log of, not natural log of 2. And it does the exact same math. So just wanted to show you the two different ways that we can kind of put these problems if you had a log and you just needed to put into the calculator about the different ways. So notice that, you can think the base b is the bottom number. So that base is always on the bottom. So we do have some properties that kind of help us out here. So if we have log base b of b to the x power, so the log and base are the exact same, our exponent is our answer. Same thing happens if it's in an exponential. If we have the base of an exponent and the base of the log are the same, that number on the inside of the log is our answer. We have a multiplication property of logs. That means that if I'm multiplying two things on the inside of that log, I can actually take it apart and add those logs separately, or vice versa. Didn't we talk about something where if we multiply, we add? Yeah, exponents. Exponents and logs are inverses of each other, so they go by the same rules. So if you have like bases and you're multiplying them, you can take them apart and add them. Same thing with division. If we're dividing them, we take them apart and subtract them. And that power property that we've been using already, where if we have that exponent inside of that log, it comes out and becomes a coefficient. So let's get a little bit of practice going on here. So my goal here is to get the base of the log and the base of my exponent to be exactly the same. So I need to change 8 root 2 so that it's base 2 and has an exponent. So 8 is 2 cubed. The square root of 2 is the same thing as 1/2. Well, if I'm multiplying like bases, I add their exponents. So we get log of 2 equals 3/2, or 7 over 2. So 2 to the 7/2. So again, since I have a base of the log and the base of my exponent the same, my answer is simply just 7/2. Again, Fractions are always the best. If you want to put 3.5, that's fine, but understand most times we're looking for exact answers, which is a fraction form. Now, a lot of students get afraid about natural log or log natural. That's why it's ln, uh, log natural. This natural log is the same thing as this log. It's just that it's base e. So ln is the same thing as log base e. So mathematicians always like to write as little as possible. So ln and log base e are the exact same function. So that means this natural log has kind of a base e. So I need to get this to be base e in order to kind of do my power property. So how do I do this? Well, the square root of e, that means it's 1/2, but since it's in the denominator, that exponent is negative 1/2. So since this natural log is a log of base e, that natural log and exponent have the same base, so our exponent is our answer. And number 3 kind of looks a little crazy because we have a whole lot of stuff going on here. Well, what we want to do is we want to start on the innermost part of this first. So 2 log base 2 of 5. Hey, that exponent base and that log base are the exact same. So what I get left with is what is on the inside, which we talked about up here. It's x. So inside of this parenthesis, we just get 5. So 4 log base 2 of 5. Okay. Now I'm going to do a little crazy thing here where for me to be able to simplify this easily, I'm going to get the exponent and the log to have the same base. Since 4 is base 2, it's 2 squared, I can then change it to look like this. So that 4 is 2 squared. You can put that in parentheses if you want to and being raised to the log base 2 power of 5. Well, if I can take an exponent and bring it out and become a coefficient, I can actually go the other way too. If it's a coefficient, I can bring it inside and make it an exponent. So then I end up getting that 2 goes inside as an exponent, so we get 5 squared, which is 25. Hey, my exponent and log have the exact same base, so the number on the inside is my answer, 25. Okay. So again, looking at the innermost and going from there, same bases, inside number is our answer. We needed to change the base here, make that an exponent, and then we have the same base in our log and exponent. All right, so for this next problem, what I'm going to actually do is for us to be able to simplify this easily, because this kind of number on the inside is base 2, but our base of our log is base 16. So there's no way of changing this base or changing what's numbered in here to base 16. So what I'm going to do is I'm going to set this equal to x. So there's a couple of different ways you can do this. You can put a base of 16 on each of these, or you can do what we call the log roll. I'm going to take the base of my log, raise it to what it's equal to, and then set it equal to the number on the inside. So that looks like 16 to the x equals to 4th root of 2. That's the log roll. Again, if you take the base of 16 and put these as exponents, you kind of get the exact same thing. 16 raised to the log base 16 of this is just that. So now that I have it set up like this, I can now get everything to be base 2. 16 is 2 to the 4th. 2 is 2 to the 1. The 4th root of 2 is 2 to the 1/4 power. So I can add those exponents. So 1 plus 1/4 is 5/4. And then we'll just set 4x. So now that we have the same base, we can set their exponents equal to each other. So you end up getting that x is 5/16. So again, we did this process here because this base 16 is too big for what's on the inside. The inside is not base 16, it's base 2. That means it's some power of 2, which we found out was 5/4. Okay, what about number 5? So I can't do any simplifying here because 5 is not base 10. That means I cannot raise 10 to a power easily to get 5. But what I do have is that power property, that with that coefficient in front of the log, I can bring it inside as an exponent. So I can rewrite this as log base 10 of 25. Well, 4 is not base 10. It doesn't have a coefficient, so we're just going to leave it as 4. But then this 1, if I'm going to simplify this to maybe one log or one number, they all should be log base 10. So how would I get this to be 1? Well, log base 10 of 10 to the 1 is 1, because again, a base of a log, base of an exponent, the exponent is our answer. So if we want to make a log base 10 equal 1, we do log base 10 of 10 to the 1 power, or just 10. Well, now that they're all log base 10 and they're all being added together, what happens to these logs if you're adding them separately? Well, that's the multiplication property. If you're adding logs separately, you can, with the same base, you can actually put them together by multiplying all the numbers on the inside. So I'm going to have log base 10 of 25 times 4 times 10, which ends up being 1,000. Well, in this situation, this 1,000 is a base 10 problem or answer. 10 or 1,000 is 10 to the third power. Wait a minute, my log base and the base of the exponent are the exact same thing, so your answer is the exponent. Okay, so don't be too afraid of logs. Yes, they kind of look weird. There's a lot of writing going on, but they're the exact same laws that we have for exponentials. They just have this weird log thing on it. So number 6 is kind of the same thing. Log natural is a log base e. Here, I could have actually left off those base 10s if I wanted to and just wrote log. Those are default base 10. So in this situation here, again, we have a coefficient in front of the log, so I can bring it on the inside and create it as an exponent. So 2 to the 4th power is 16. There's no number in front of this natural log of 3, so I'm doing it like that. And then for 1, how do I do that? Well, again, we're going to do what we did here. So since natural log is base e, so I'm going to use the base of my exponent to be the same as the base of the log. And again, in that situation, the exponent would be my answer. So if for some reason this number was 2, what would we put here? Well, natural log of e squared. If we're subtracting 5, it would be natural log of e to the 5th power. Because again, natural log is log base e. This base of the exponent is e, so our exponent is the answer. So what do I do when I'm subtracting them? Well, if you subtract the same base logs from each other, you can actually put the numbers on the inside together and divide them. So I'm going to do 16 divided by 3 divided by e. Well, if I'm going to do that, it actually ends up coming out to being 16 divided by 3e. And that's all inside of that natural log. Well, since there's no way of making 16 over 3e be base e, our answer is just this. All right, so this next problem is kind of doing the same thing that we've been doing. Now notice that they're just logs, so these are default base 10. So you can put a little 10 for the basis for each of those if you want to. So we're going to do the same thing. So coefficient in front of the log goes in and becomes an exponent. So we have 5 squared, which is 25. Nothing happens here. And that's already has a log base 10. So sweet. So what we're going to do here is we're going to follow the order of operations and go from left to right. So since we're adding these logs separately, I'm going to put them together and multiply them. But then since I'm subtracting this log of 2, I'm going to divide all that by that. So you end up getting log of 100. But, again, logs are default base 10. 100 is a power of 10. It's 10 squared. So base of the log, base of the exponent, the exact same. Our answer is the exponent. So recently we added this problem in our notes because we were just trying to make sure that you remember all of the algebra that you should know from Algebra 1 and Algebra 2. So if you were going to solve this using logs or exponents, you would need to make sure that you isolate the variable. Well, right now there's a 1/4 in front of this e to the 2x, which we need to get rid of. And to get rid of 1/4, I'm going to multiply both sides by 4. So you end up having e to the 2x equals 36. Well, then what we're going to end up doing, and I need some room here, so I'm going to put 36 a little off to the side here. In order to get the exponent out of the exponent, the variable out of the exponent, I would need to log both sides. And since we're dealing with base e, it's going to be better if we natural log both sides. Well, if I natural log both sides, natural log of e to the 2x is just 2x. And then we have natural log of 36 that cannot be simplified any further. Then I solve for x by, you could divide both sides by 2, but what I'm going to do is half both sides and end up getting 1x equals, well, if we have a half outside as a coefficient, it goes in as an exponent, which 36 to the 1/2 power. And then that is almost like square rooting 36, and you end up getting the natural log of 6, which some of you are like, wait, we solved by square root. No, we didn't. We just asked you for the square root of 36. And also, you can also think, well, if you square root 36 and get plus or minus 6, can you have negative arguments? No. So our answer for this is just the natural log of 6. All right, so in this next problem, I'm going to do this a little differently than the log roll. Maybe this might help people not make too many mistakes here, because when I give this out to students, a lot of students like to go from the inside and go from there. But actually, when we're dealing with this, we want to go from the outside in, kind of different than what we do usually. So what I'm actually going to do for this problem is I'm going to use my exponential power rule here. So what I can actually do is take both sides of those equations and treat them as exponents. So I'm going to put a base 2 on each one of those. Why 2? Well, look at what I did. I have a base of my exponent to be the same as the base of this log. So those end up canceling out, and we're left with what's on the inside of that log, which is log base 3 of log base x of 64. Equals, well, what's 2 to the 0? Well, always remember that any power of 0 is 1. It's not 0. That's what a lot of students like to do. So what do you think I should raise both sides to now? Yeah, I'm going to put 3 as my base and treat those each as exponents. Why 3? Well, now the base of my exponent and the base of this log are the exact same thing. So we're left with what's on the inside. So 3 to the 1 power is 3. So again, I'm adding bases here and treating what each of those sides of the equation as exponents. So you can almost do the exact same thing here. We can do raise each to the x and get that the base of this log or base of this exponent and the base of the log are the same. So we get 64 equals x cubed. You can cube root both sides, or you can ask yourself, well, what power of or what's 64 to what power is being raised to the third power, or all that stuff. And you can end up getting that x equals 4, because 4 cubed is 64. Now be careful that sometimes this could be plus or minus. If it's squared or it's fourth root or an even root or something like that. Also pay attention that for this situation, our base of a log, that x has to be greater than 0, but not equal to 1. Okay, so make sure you remember those rules that we talked about on the first side of our notes. All right, what about this next problem here? Well, both of these logs have the same exact base and they're being added together. So I can actually combine them together by multiplying their insides. Well, what I'm going to do is I'm going to apply what I did over here on this side. So you could log roll. It's going to be the exact same thing. Just I'm going to try this differently, see if students understand it better. So I'm going to take each side of the equation and take them to a base 6 so that the 6 and the log base 6 cancel off, and we're left with distributing in that x equals to 6 to the 1, which is 6. Well, if you're solving quadratics, you need to make sure it's equal to 0, and you factor it and you solve it, you end up getting that x equals -3 and 2. Now, we've talked about problems where we have these extraneous solutions. We have solutions that might not actually happen. In logarithms, the number on the inside has to be greater than 0. So we need to make sure that this x plus 1 is greater than 0, or that x is greater than -1, and x is greater than 0. So it has to apply to both of these. So pretty much our x has to be positive, which -3 is not. Another way you can do this is plug it in. Well, if you plug in -3 here, you get -2. You can't take a log of a negative number. Definitely, if you plug in -3 there, it doesn't work. So not always does the negative x not work, but just make sure to check your answers. Don't put both of them on there. You need to make sure that it actually makes sense. All right, what about this next problem here? So since I have a coefficient in front of this log, I'm going to bring it in and make it an exponent. So log base a of 3 squared, which is 9, that's an a, and log base a of 5. I wish I was better at writing those little fancier a's with a little loop on the top. All right, well, since I'm adding two logs of the exact same base, I can multiply their insides. So 9 times 5 is 45. So I have log base a of x equals log base a of 45. Well, since both sides of this equal sign have a log base a, we can drop those logs and end up getting that their insides are equal to each other. So we end up finding out that x is 45, which makes sense because x will have to be greater than 0 in this case. That's how logs work. You can't do a log of a negative number. So what about number 11 here? Well, for number 11, if we do the log roll, which might be easier to see here again, we could do x to those powers if we wanted to. We get x to the 1 equals 1. Well, what do you raise to the 1 power to get 1? Well, 1. So is that my answer? No. We have to be very careful that the base of our log in this situation is greater than 0, but not equal to 1. Well, that means that this solution doesn't work. So what's my possible answer? Well, there isn't one. This is a no solution problem. All right, so for 12 and 13, the way that we're going to solve these is we're going to kind of do what we did for 8 and 9. We're going to have these be treated as exponents. Now, it is very careful. You have to be very careful with what number you choose. We have a base 9 and a base 3. If we raise each of these as a base 3 problem, you're not going to get rid of this exponent. You're going to actually make the problem a lot harder. What we want to do is we want to actually pick the bigger of the two numbers. And we always set up these problems so that it actually works out in that way. So what's nice about here is that we have now a base of an exponent and the base of the log. They're the exact same. So we're left with the number that's on the inside. Well, the problem on this side is that I put this base 9 here, which is not 3, but I can make 9 base 3. I can make that 3 squared of log base 3 of x plus 1. Well, this is 2 times log base 3 of x plus 1. So that number, that coefficient goes in and becomes an exponent. So just so that I'm not skipping too many steps, we end up getting this. So again, coefficient goes in as an exponent. Now, 3 and log, this exponent and this log have the same base, so we're left with what's on the inside. Well, on the inside, we're left with x plus 1 squared, which is x squared plus 2x plus 1. been doing a lot of foiling with all our classes and still having people that are messing that up and telling me it's x squared plus 1. So I'm going to move that to everything to one side. So we end up getting x squared minus 4. And, you can factor it, solve it, move, the 4 over, and you end up getting that x is plus or minus 2. Now, be very careful with logs. We have very strict restrictions on this. If we plug in 2 into each of these, do you always get positive numbers? Yes. If you plug in negative 2, do you always get positive numbers? In here you do. Negative 4 plus 1 is 5. But over here, negative 2 plus 1 is negative 1. So that means negative 2 cannot be an answer. So x can only be positive 2. So 13, what number should I raise those to? Hopefully you said 16. So I'm going to take those to 16 of that power. Why 16? Well, if I change 16 to base 4, I end up getting 4 squared times log base 4 of x minus 1. On this side, base of the exponent, base of the log is the same, so we're left with what's on the inside. So kind of this does what we did here. We're going to bring that in as an exponent. The base and the log cancel out each other, so we're left with x minus 1 squared equals 3x plus 7. Okay, so again, coefficient goes in as an exponent. So then we'll do some algebra. We get x squared minus 2x plus 1 equals 3x plus 7. Move everything to one side, get x squared minus 5x minus 6. And for some reason, for all students from Algebra 1 to calculus, we all have a problem with factoring out something like this. I get a lot of 2 and 3s as answers, and you have to be very careful and remember that 1 is a possible answer. So negative 6 times negative 1 is, or positive 1 is negative 6, and when you add those up, you get negative 5. So we get that 6 and negative 1 are our answers. Do they both work? Well, 6 works. That gives us 5. That gives us, I think, 25. If you plug in negative 1, we get negative 2. Nope, doesn't work. So our answer for that one is only positive 6.